Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
Distributed loads are common in engineering. For example, the self-weight of a beam is a constant distributed load commonly referred to as a uniformly distributed load, or UDL. The water pressure in a dam increases uniformly with depth and is known as a uniformly varying load, or UVL. Some distributed loads are very complex, for instance the wind pressure on a building. This video will use simple maths to reduce three types of distributed load to an equivalent single load. The techniques used can be applied to other types of distributed load. So let's get to it. We will start with a uniformly distributed load, a UDL, of W kilonewtons per meter acting over a length of L meters. Our objective is to determine the magnitude and location of a single force that is equivalent to the UDL. I know this looks like a waste of time as we know the answer. The force is WL kilonewtons acting at the centre of the beam. I get that. But not so fast. This example will lay out the maths needed to investigate more complex types of distributed loads. Consider a small element of the load. The element is x meters from A and is dx wide. The element contributes a force of W dx, and summing the force for all the elements will yield the total load. Integral calculus is the tool used to sum together lots of little elements. So we need to integrate W dx for all elements in the load. The integral of W dx is Wx, and applying the limits shows the total load is WL kilonewtons, as expected. Next, integrate to find the moment of the load about A. The moment of the element is the element force W dx times its lever arm x. Integrating the moments for all the elements in the load shows that the total moment of the load about A is WL squared upon 2 kilonewton meters. By definition, the moment of the distributed load about A is equal to the magnitude of the load times its lever arm. And this shows that the lever arm of the load is L upon 2 meters. Again, as expected. So we have proved that a single force of WL acting at the centre of the UDL is equivalent to the UDL itself. We will now apply the same techniques to a triangular load that varies from 0 at A to W at B. This is a uniformly varying load, a UVL. Again, consider a thin element of the load x meters from A. The intensity of the load on the element is Wx upon L, so each element will make a contribution of Wx upon L times dx towards the total force. Integrating the force contributions from all elements shows the total load is WL upon 2 kilonewtons. Next, integrate the turning effects of all of the elements about A to show that the moment of the load is WL squared upon 3. Finally, equating the moment of the distributed load to the equivalent force times its lever arm shows that the lever arm is 2/3 L. This proves that a single force of WL upon 2 acting 2/3 of L from A is equivalent to the UVL. The results from the UVL probably came as no surprise to you. The next load varies parabolically from 0 at A to W kilonewtons per meter at B, and here it is not so easy to know what to expect. However, as engineers we should be able to make sensible predictions based on the results from the UVL. Pause the playback and think about it. We see that the parabolic load is consistently less than the UVL, so the total load will be less than WL upon 2. But how much less? Inspection of the two loads suggests that the resultant parabolic load will lie between WL upon 4 and WL upon 2 kilonewtons. It is also reasonable to postulate that the lever arm of the parabolic load will be greater than that of the UVL. It certainly looks that way from the diagrams. Anyway, enough speculation, let's get down to the maths. The load is parabolic, so the intensity of the load is at x is Wx squared upon L squared, and each element will make a contribution of Wx squared upon L squared times dx towards the total force. Integrating the force contributions for all elements shows the total load is WL upon 3 kilonewtons. Next, integrate the turning effects of all of the elements about A to show that the moment of the load about A is WL squared upon 4. The moment of the distributed load equals the magnitude of the load times its lever arm, so the lever arm must be 3/4 L. In other words, a single force of WL upon 3 acting 3/4 L from A is equivalent to the parabolic load. And that concludes the analysis. If you would like free, printable, annotated notes for this video, then swing by Dr. Jim's website at drjimstructures.com. In the next video, Dr. Jim will investigate the moment or turning effect of a distributed load about a point. It's amazing. Be sure not to miss it. There's a link on the screen. Well, thanks for watching. If you found this video useful, please give it a like. And feel free to comment. Your feedback is appreciated. Bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.